Thank you very much. So first I would like to thank the organizers for inviting me. It's my first time in CIRM, and I really heard a lot about it, so I'm looking forward for this week. And looking forward to talk with people and meet you all. I also thank to my fellow speakers because they introduced some stuff that I may just briefly go through that you have already understanding, so it's very helpful. So if I tend to speak very loud, so if it's too loud, just let me know. And I tend to speak fast, but if anything, just interrupt me in the in between. So I will try to. My background is in numerical linear algebra. So I'm applied mathematician with a background in computer science. So I'm mostly interested in algorithms, algorithmic developments, efficient algorithms for various applications. And that's the kind of also the perspective that I take on the quantum algorithms. So I will try to introduce some concepts which hopefully will bring us to this quantum computation or quantum scientific computing, hopefully in near future. And I just wanted to mention that Paul, who is a mathematician but also my husband, so he participated a lot in preparing the slides because he was taking care of our little one, that I could focus on this. So thank you, Paul. And I would like to thank for the support of the work over the years from Virginia Tech, National Science Foundation, but in particular the things I'm going to talk about today were heavily connected to my research fellowship at Institute of Pure and Applied Mathematics and University of California in Los Angeles last fall, which is a whole long program on quantum computing. So a lot of great connections and great research. So I will first talk about some motivation and set up some notation. Some of you may have been familiar with the things I will be talking about. Some of you may not, but I just want to make sure we are thinking and talking about the same things. Then I will start with, of course, when we are talking about quantum, the name of Feynman has to appear at some context. So many years ago, Richard Feynman already kind of indicated that the quantum is the way of looking on problems, and finally we are at the stage that we are closer to maybe make it more realistic for various applications and simulating a lot of interesting problems using quantum computers. And of course, his focus was on applications in physics, but we know we can do way more at the moment. So there's a lot of materials available, and when I was preparing this lecture, of course, I look at many of the concepts and many other materials and general introductions from the literature. I was privileged to work during the program with Di Fang and Lin Lin, which had already opportunities to teach the classes in their institutions. In terms of Qiskit simulators or quantum computers, a lot is also available by multiple companies who are working on that actively, in particular IBM Quantum Platform, which has a lot of materials also for learning, and a lot of classical references, but just to give you a little bit a brief where to start if you're starting your journey with quantum computing. Okay, so this is the prereq for the class and for the lecture, and Lucy is on the back, so if you want to consult, you can always ask it. We have been actually complaining that there's lots of baby books in physics and statistics and quantum computing, but we're looking for those in math, and there are some related, but these are really, really basics which we got from our physics friends for our daughter. So if you want to teach your little ones to be up to date in a couple of years, that's a good start. Okay, so I will just do a little bit of history. We heard a lot of names already. So it all started in the 80s, actually, where Feynman and his collaborators were already talking about the possibility of computing power beyond the analog or classical computers. At that time, it was all a dream. In a sense, they started to think about it and see what is possible, but we were still far away from actually realizing the qubits in the physical space. And then what is considered a big, one of the first, I think there is no agreement. A lot of people are talking about 3 founding fathers of quantum computing: Deutsch, Feynman, and Shor, but there's lots of people who have been involved. But then in 1985, there was a first attempt on discussion by Deutsch about the quantum Turing machine. One of the first algorithms in 1992, which was actually a very simple algorithm, which is considered to be one of the first quantum algorithms, which essentially could determine if a function is a constant function or a balanced function. So very simple problem. That's how it started. And then in 1993, the field of quantum complexity theory, which is very rich, kind of started with this, the work of Bernstein and Vazirani, a lot of other people involved. Simon in 1994, a polynomial time algorithm for a quantum computer. So we started to go into the direction of really a quantum algorithms. And of course, Shor in 1994, really first efficient quantum algorithm for the problem of integer factorization, discrete, and discrete logarithm, which was mentioned by my predecessors. And then a big kind of breakthrough recently by Google to justify the quantum supremacy on their big experiment of 53 qubits. So you see the timeline, like it's over 30 years, how it all started from very theoretical investigation. Actually, we now go to the step where hopefully in our lifetime we may see actually, and there are some simulations, but maybe some more efficient and really bring it to the point that we can do calculations. So as I mentioned, in my perspective on when I got kind of involved in quantum computing, my question was, I'm a person who develops solvers. So a lot of applications in engineering and in many other disciplines in quantum chemistry and so on. At the end, we need solvers for like basic linear algebra problems. So my question from the beginning was, what actually can we do? What algorithms we can, how we can think about algorithms designed for those machines. And the short answer there will be very, very different. We can draw from some prior knowledge, but fortunately and unfortunately, quantum algorithm and quantum field is very different. Very different in the sense that we have to change our way of thinking. Not everything classical transforms directly to the quantum world, which is good for us because there is lots of interesting research. But it's also, in a sense, challenging because we have to kind of take our classical hat off and start working in very different framework. So I will just give a brief overview on some basic stuff. So for some of you, it may be boring, so stay with me. I will try to get to more interesting things, but I just want to make sure that we are all on the same page. And I have heard that some people here also are not necessarily super familiar with quantum computing, so I hope that will benefit those of you. So there are 4 main postulates of quantum mechanics, and this morning we already had like a crash course in quantum mechanics. The state-space postulate, which is We are usually dealing with a quantum state, which is a superposition of the classical states. And we can usually write it using our kind of linear algebra notation of vector of amplitudes, and then we can try to apply measurements or apply some operations. And as we will talk about, these are very, very restricted. So we are limited to unitary operations, and there is this great way of thinking or illustrating, you know, when we talk about classical computer, we think about bits, and the bit has always values 0 and 1. But when we talk about quantum computer, we immediately go to a different concepts. We go to qubits, which are kind of this superposition. They're in very different state, and depending what's going on, and even measurements, as we heard, are changing those. So it's a very different object that we have to learn to deal with. Also the notation, as I said, I come from numerical linear algebra, so one thing, first thing which was moving to quantum world is like moving to Dirac notation, which is like, you know, the different way, and those of you who have been trained from the beginning, it's easy, but when you move from classical linear algebra, it's sometimes like, okay, is it a vector or is it a row vector? Or so to give you just a brief, we will be using the cat notation for a column vector. And as I said, these are, you can think about the vector which has amplitudes, and then the row vector. And of course, we have a classical notation about conjugation of the quantum states. And then we have the bracket notation, which is essentially what we understand from the linear algebra, the inner product. So the row vector times the column vector, and we can get a scalar. And during this talk, we will assume that the state is normalized. So we have a nice space to work with. So C to the power n, capital N, when capital N is 2 to the small n, so small n is the number of qubits. And we have an associated 2 norm with respect to which we normalize. So we will have a set of quantum states which give us the state space. So this is the space of the objects that we are going to work with. And as you saw, it's a complex vector space with an inner product and the associated norm. If it's a finite dimensional space, then as we already it's isometric to the C to the power n, as I mentioned before. So we are going to use that without the loss of generality that we can always take h to be C to the power n. And where n, the small n, is the number of quantum bits, so qubits. I think it's always good to kind of try to visualize things, how we think about many concepts. And you will be using Qiskit, or you have been using Qiskit already. So you can use the block sphere to represent different states if they're directly representable, or different bases. We have number of bases we can work with. The classical ones, so 0 and 1 state, which can be represented by the following vectors and visualized in the x, y, z space, but we can also have bases plus and minus. There are different ways how we can represent, and you can explore that using Qiskit and do nice visualization. So can be useful if you try to understand the concepts. And then we had already talked about the probabilities and measurements. So if you want to measure, so if we have a quantum state, it's usually represented in terms of the bases. So here we have this basis 0, 1. So we have A and B as the amplitudes. And the normalization, as I said, the normalization implies that there is a following relation between the amplitudes. And if we perform a measurement, we will get the state 0 with the probability A, absolute value of A square, and the other one with the probability B to the square. And of course, they have to sum to 1 as the probabilities. So very simple example, right? If you have the quantum state with 2 amplitudes and you measure the probability, in this case, the probability of measuring 0 and 1 is the same. It's 1/2, and they sum to 1. So very trivial example, just to think about how we look on these problems. Another notation which you have already seen, it's the Kronecker product, but there are different sources use different notations sometimes. So if you think about Kronecker product of M states 0, so it can be sometimes denoted by 0 to the power m, or you take cat and then you do the Kronecker product m times. This is how you may see it in literature. Exactly identity, we usually will use bold for the matrices or operators. So here is the identity matrix of size m by n. I will skip the sizes if the size is kind of obvious from the context. We can think about the jth column of the identity matrix when we think about the standard basis, and the binary representation, which we will be working with of J, is also given in the standard notation that, well, standard for this talk. So the second postulate is, so we have the state, and I said we always have a state, and then we can do something. We can apply the operator to that state, and in particular, we are interested in quantum operators. So we always we look on the evolution from one quantum state to the other, and this can only be achieved using the unitary operator. So unitary transformations are those which are allowed in the quantum world. So if we want to look on how the state psi transfers to psi prime, is just we represent the mapping by the unitary operator. The unitary matrix is very often, it's referred as gate. It's the gate representation or gate realization, and you have heard about gates already today many times. And the operator acting on the n-qubit quantum state space is called an n-qubit operator. So these are kind of very classical things. So some of the unitary operators you have seen, and corresponding gates as well, are the Hadamard classical Pauli matrices, so X, Y, Z. We will use some rotation along different directions, so rotation matrices, again, classical linear algebra object also here. And phase, there's different notations. Sometimes we describe phase operator as S, sometimes as P, depending on what are you reading. And then we have 2-qubit operators. So we have seen maybe this controlled NOT operator. So it's a NOT operator with control when it will be applied and to which qubits, and the swap operator. So as you see, these are unitary matrices of proper sizes depending on the number of qubits. This is a 2-qubit operator, so it's 2 to the 2, so the matrices are of size 4 by 4. Then the quantum measure postulate, so projective measurement. So as we have seen from the picture, we are having bits on 0, 1, and we have qubits. So if we measure a quantum state, we cannot see the superposition of those two classical states. So we cannot really see the state of the qubit. We only can get the classical state. And this is, I think, a pretty illustrative picture when we think about the input in the classical computer. We have 2 bits. With classical computer, there's something, it's 0 or 1, and the output will be 0, 1, where when we think in terms of quantum computer, we have the superposition of 0 and 1, which we cannot actually see. But the output will be always the classical state. Okay, we also, one thing, which is we don't know in advance which J, so which classical state we'll get. We know only the probability of observing each of them, and that was already also mentioned, the Born's rule, which is kind of very unnatural at the beginning to think in terms of outputs of your algorithms. So yes, we talk about the specific phenomena. You have heard if we measure a state, the state disappears itself, and we only are left with the classical bit outputs, and the state kind of collapses into the classical state, which we can observe. So quantum observables in finite dimension, they always correspond to Hermitian matrix. So that's what the observables are. And we have been, you have seen it just in the previous talk. And the output of the measured in this quantum state by a quantum observable is an eigenvalue. And that was what was also the basis for the adiabatic algorithm and variational eigensolver. And we can measure, of course, the expectation value, which is nothing else as a M inner product, where the inner product is induced by the matrix M. And then the last, so these are the four postulates. The last one is that an element in the n-qubit state space can always be decomposed as a linear combination when we have the amplitudes and the classical states. And then, again, the notation, you can think about the quantum state using the amplitudes. You can represent it as a Kronecker product, and then they're sometimes collapsed to each other, or they're written in this way. So all these objects are describing the same thing. Sometimes when reading, it's really confusing. So at the beginning, so I just wanted to make sure these are the same thing. And we talk about the bit string representation in the sense of classical computational basis, so standard basis or other basis in this complex space, vector space. Okay, so again, just very simple example on that. If you have 2-qubit system, then we know how the space looks like. These are the standard bases of this state space. Again, we can represent all the elements using the Kronecker product representation. However, not all quantum states can be written in this form. So there are some states which you cannot write as a Kronecker product in this fashion. And one of the famous one is the Bell state, or the EPR pair, which has this representation, and you cannot really decompose it in this way. It's also one of the kind of a cute little exercise if you want to do with Qiskits, how to actually do the Bell state simulation. Okay, so when we have the quantum states and operators that we are going to use to evolve the states, we will have also the representation of this, what is actually happening with our input and our in between inputting the information and getting the output through measurements, or is the quantum circuit. So this is how we actually realize those. We build quantum circuits, and then depending on the hardware, these are physically implemented, and our algorithms or our procedures can be executed. So those of you, you have seen some quantum circuits. I will use the notation that ancilla qubits, so sometimes are also said, okay, these are the kind of garbage or extra qubits that we need. We always want to have small number of them. I will denote those to be on the top, and then system qubits, which actually we will use to encode the state, will be on the bottom. And then as you see, there will be some unitary operations in between on some other of different types, maybe between one qubit, many qubits, or just on the single qubit. And then there will be a measurement, and the result will be the result of applying a lot of this unitary operations on those qubits. And we talk about the operators, and then they have, of course, associate gates. So these operators are also realized through gates. So we have Pauli gates, how they act on the single qubit, on the 2-qubit system, Hadamard gates, controlled nodes. So it depends on which qubit is the control qubit, and the swap. So how these look like, and how we look on the results of those calculations if we apply any of those operator gates. Okay. So we have a notation, and now we will go into quantum numerical linear algebra. So those of you who are entering the field or are interested, a lot of people will tell you that quantum field or quantum algorithms, quantum computing, is really heavily based on linear algebra. So as all of you have some background in linear algebra, I'm wondering how many of you have a background in numerical linear algebra? You took any classes in numerical linear algebra? Okay, so some of you did. Some of you may have learned by yourself. It's, self-studying is also a good way of learning things. But a lot of things that we have already, you have already seen. And when, I was sitting in the back and I was like, okay, this is this in numerical linear algebra. This is this in numerical linear algebra. So there is a lot of correspondence from techniques that you know or you may know from the different contexts. And in particular for me, it's numerical linear algebra. So let's just talk about, what are the expectations and restrictions when we want to, at the end of the day, as I said, if we do any applications, and if you think about, Hamiltonian simulation, dynamical system, control, at the end of the day, like we start with infinite dimensional, so we go through like PDEs, differential equations, and so on, but eventually we have to discretize things. So we are coming to discrete world. So the world when the data has to be represented in a discrete way, and lots of algorithms are using the discrete formulation. And those are actually linear algebra problems, but solved using computers, and either classical computers or in the future using quantum computers. And from linear algebra to numerical linear algebra, no one is solving a linear system in practice using Gaussian elimination, right? So these are nice, cute tools, but in practice, we have way more powerful methods to solve a lot of practical problems. So we'll talk about some of them. So quantum computers are known or are expected, and that's what their power is, exponential quantum speedup for some problems. And it's very natural for us to think about it, how we can solve linear algebra problems. So the classical problems that I will be thinking about are solving linear system, executing, like evaluating functions of matrices or operators, solving least squares problems, so optimization problems as well, and eigenvalue problems. And we have seen those problems today in various contexts, ground states, calculations, nothing as calculating one of the dominant eigenvalues as a linear algebra problem. So these are the concepts that are very interesting, and at the moment, a lot of how I look on the quantum computing, a lot of problems are coming from the nature of quantum chemistry or physics, because these problems are kind of very nicely transferable from the setup as they are in physics and chemistry to the quantum computer, because they use the same objects. They will use, you will think about like electrons, we think about ions, and this is very nice. But and I think at the moment the most progress that we will see and we are seeing in quantum computing are for those problems, and problems in quantum chemistry and physics, because they are kind of very nice correspondence between the hardware and the implementation of those algorithms with respect to the application. But at the end of the day, and it's already happening, people want to do quantum algorithm computing for machine learning or other problems where your data are given by set of points, given by matrices, which don't have a nature connecting to a particle or energy, or very often to anything that we can think about in terms of physics and chemistry, or nice atoms, electrons, and so on, or any kind of quantum particles. So what can we do when we have those problems, but the applications may be different? So that's how linear algebra people look on the quantum computing at the moment. How we can benefit from the exponential quantum speedup for the problems that we need to provide computational tools for other disciplines. So the typical cost of classical algorithm, if you do some complexity theory, for capital N dimensional system, and remember for me capital N in terms of relation to the quantum is 2 to the power n, where n is number of qubits, is polynomial in n, versus the expected one is polynomial in the logarithm of n, a cost for quantum algorithm. So in terms of dimensions, and if we are talking about dimension n, we are usually talking about huge dimensions in applications. So going from the polynomial to the polynomial in the logarithm is a huge gain in terms of complicated simulation. So there are some theorems which are a little bit pessimistic, but we can still do things. So at the beginning, it will sound a little bit pessimistic. So when I started to learn about it, it's like, oh, great. So what we actually can do. So the first one is the known cloning theorem, which was stated in 82, which basically says if we have two quantum systems, there is no unitary operator. Remember, we are only allowed unitary in quantum world. That follow the normalized states. So we have two normalized states that we can transfer. We can apply this unitary operator to this is again the notation, the Kronecker product of these two states, and get essentially the copy of the state. So there is no possibility of kind of copying the data or your information on the way. So this theorem, there is this no cloning theorem, forbids it from generic quantum copy operation. And if you think from the eyes of numerical linear algebra people, depending on trying to develop practical algorithms, if we cannot copy or create a copy of the state, that's a very limiting property. We cannot do any iterative methods, which are the tools for large problems. If we want to solve big practical problems, we have to be able to use iterative algorithms. But if we are not able to copy, those algorithms are out of the view. I mean, we cannot use them. Typical, the out-of-the-shelf approach is not even feasible. So that's one. So there are two exceptions of this non-cloning theorem. So if we know how the quantum state was prepared, so we not only know the quantum state, but we know how exactly we got it, then we can create a copy on the way if we need to do it. But again, very often, if you think about application, we are not having the whole pipeline very often. It's not that we are like, okay, we have a physical problem and then we get the data and so on, so I can trace all the information. Sometimes we are the last group in the chain, and we are not even seeing what the problem originally was, which is very limited. So the controlled NOT gate also enables copying classical information. So as long as we can copy classical information, we cannot copy the quantum state, but we can copy some classical bits. However, we cannot use the copy of the superposition. And this is a very simple condition. So if I have a Kronecker of the state psi with the zero state, and then I apply the control NOT, which I can do for the classical states, and I will get the copy. If I apply it to one of the states is not a classical state, it's a quantum state, then this is not the same as just taking a copy, the Kronecker, so creating the copy of it. So I cannot use it in the quantum state. And the other result, which is consequence of the non-cloning theorem, is no deleting theorem, which says there is no unitary operator such that I can kind of annihilate information or zero out something using the unitary operator. All right, so given 2 copies, it's not possible. So how we are supposed to do practical algorithms, knowing what we know with those limitations. So first, one of the biggest problem in practice is how you can get your input data into the quantum computer. And in certain applications, and Hamiltonian simulations are one of the big applications, they're kind of a nice ways of doing it because the Hamiltonians you can directly represent using nice unitary operators. So your Hamiltonian may be a linear combination of the Pauli matrices. These are already unitary, great. We know how to apply unitary, so how to build circuits to kind of input that Hamiltonian into the quantum computer and then do simulations. But what if we are not in this situation? How to input your information? And in particular, again, as a numerical linear algebra, okay, for me, the basic model is the matrix and a vector. That's how I think about the world. These are either vectors or matrices or tensors, which are generalizations. So how I can input the vector or matrix into the quantum computer? And so to give you a context, why is it so important? So when we were attending the program at UCLA, we talked with some people who try to use quantum computing for really important medical simulations. And one of the professors from computer science department who has a big project actually on achieving this, we talked with him and they spent essentially several months trying to figure out how to input the data which they have from medical trials, how to even input that into the machine and then be able to do something. So this is really non-trivial problem. And you can think about it, we still are working on efficient ways, and I will talk about that, efficient ways on just putting your basic data, your input into quantum computer. So from that being already complicated, then we have to do the simulations and be able to do it without introducing too much error and so on, that we actually don't get the garbage. It's really a challenging problem. So how do we input the data? So for us, like, how do we input a model for a vector? So again, the n-qubit quantum state can be viewed as a vector in the space 2 to the power n with a normalization. And the cost of storing this n-qubit quantum state is proportional to n. So there is, of course, the cost associated with storing. So how what we call the quantum state preparation, and there is a number of resources available about quantum state preparation, and many of them are very particular in the sense how you can maybe input a very particular vector or your very particular state. But what we are kind of have to be able at some point to do is have a black box quantum state preparation such that I can prepare any state I want. So state preparation oracle. So the goal is to construct an n-qubit state such that I can find the unitary operator that if I put something in, and usually I select very trivial state, I will be able to get my state of choice, psi, as a classical linear combination. This is how we think in terms of linear algebra, right? We always have the basis and we want to get our vector as a linear combination of the basis. So of course the amplitudes, so these are the amplitudes which will enter in your classical vector representation are unknown a priori, and they can only be accessed using some oracles. So you can only look and get them through the black box operation. each amplitude will be encoded with the n-bit precision. So we also have to make sure that we are able to encode, or we are able to put all the necessary information having those n bits available. Because if we need more bits to represent the information, and we have an n-bit quantum computer, then we are essentially losing information by just encoding. So the oracle UPSI can be invoked as required with the complexity 0 to 1, meaning we have to be able to access it and apply it pretty cheaply. If preparing the state or getting that state applying the oracle is too expensive, we also cannot do it. Because remember, we cannot copy anything. Very often we will have to, apply this operator again to get some state back. So there has been a number of attempts on looking on the quantum state preparation algorithms. And as you see, we're one of the significant contributions is in 2002. So giving a certain probability to the distribution, how to efficiently create a quantum superposition where you have the amplitudes given by this. And it was in 2002, and then for a long period, it's almost 20 years when people have been looking on the more efficient way, how to do it for general quantum states, and it's still ongoing field, how to, even in the context of the variational eigensolver, how you can get the state which has enough overlap with your ground state. I mean, you need that to even start your algorithm. So these are really still open questions and challenging, and I think no one would actually say that this is a solved problem. So then 2021, there was an asymptotically optimal circuit depth for the quantum state preparation, which was able to achieve that prepare a state without, in the theta 2 to the power n over n, depth of the circuit without ancillary qubits. So if you don't want to use extra qubits, that's what you can do. And theta of n with the extra qubits. So if you can pay for extra qubits, you can do it in theta of n, but depth of the circuit, but you have to pay the price. And then there is always a balance. What can you get extra qubits, or you are happy with a little bit different result. And then 2021, another result when they were able to reduce in terms of the depth of optimal depth of the circle, and these are actually very similar results, but achieved by different techniques and different circuits. So these are the results. If you're interested in quantum state preparation, you can take a look. And more recently, people have been studying how you can actually prepare the states with only using single or 2-qubit systems, 2-qubit gates. You want to also your circuits to be relatively simple and using only simple gates. So there has been some results for that, or for sparse quantum states, maybe for mere applications. You know that your state or your initial input has some sparsity pattern. And if you know the sparsity pattern, you can also do it more efficiently. But as I say, we are far away at the moment from having like general black box. It's all requires, or it's all based on some structure that you can extract from the nature of your problem. And then 2023, quantum state preparation using quantum signal processing. So this is one of other techniques. We heard already about the quantum Fourier transform and quantum signal processing and quantum singular value transformation are the techniques that also enable to prepare the quantum states depending on if we have capacity for extra qubits or not, and there are some other parameters that come into the game. So really extensive research. It's actually a very this one is very interesting paper, and you can see that there is a lot of parameters involved, so you have to pay, and as I said, it doesn't fit all, but for certain applications, it works quite well. So the other object, so okay, let's assume we are able to prepare our state. So we're able to prepare a state that we will put into our simulation. Is how we can actually input the model. So we need an input model for the matrix. So if our data are represented using a matrix, or you can think about operator, how we can actually put this data in. And as I said, in some applications from quantum physics, quantum chemistry, if we deal with Hamiltonians and they have a special structure, I will talk about that also on Thursday. There are kind of nicer ways of transferring those information or putting them into quantum computer. But if I have a general matrix A or general operator A, how I actually can input this data if I know that my quantum computer only can deal with unitaries? So the technique which is used for that is called block encoding. Some of you may also read about standard encoding, and they are related. I think the initial paper introduced standard encoding, and then people started to use block encoding, and that's kind of stick as a general notation. So the idea is like, okay, my matrix is not necessarily unitary. If it is unitary, that's nice. This is trivial. But if it's non-unitary, how I can input this data into the computer? So the basic idea is we try to embed a non-unitary matrix which contains our input data. And we assume that the two norm of our matrix is bounded by some alpha. Usually we want it bounded by 1, so we can always scale if we need to, into a unitary matrix of larger size. So what the idea is, okay, U of A will be a unitary matrix, which will be bigger matrix that on the top will be able to encode our matrix. So this is all your original matrix of data. It can be anything. And then there will be some extra information around such that this whole object will be unitary. So since this object will be unitary, it's feasible, in theory, to be turned into the circuit. Of course, this unitary matrix will be may be complicated, so then there will be also a way how to actually express this unitary matrix in terms of the unitary matrices which are nice and which we know, like Hadamard, Pauli, and so on. So that's kind of the next step, how to transfer first the arbitrary data into unitary, but how to then go from unitary to the circuit. So there are 2 steps here. So that's step number 2. I'm ahead of myself. Convert this unitary into quantum circuit. So how to express this unitary as a product of the simple ones, and how to do then calculation. So this is a simple circuit of general block encoding. Again, we have some ancilla qubits. We have the input. We have to provide the realization of this unitary operator, and then eventually measure how this is actually applied to whatever set of data we want. So we can come up with many ways of, encoding this, so creating this matrix. But the more challenging problem is how we can actually encode our original data into unitary matrix that can be implemented efficiently. So what I can create a great block encoding if it's not transferable to the circuit. So there is no way I can actually physically use it on my quantum computer. Let me just look at the time. How much time I have?
It's 20 past 5.
Okay. Just to make sure. So what is a block encoding? I told you the brief idea. Okay, there is a way of like putting all my data such that they will appear in the corner of some matrix. So the block encoding, as I said, initially it was introduced a little bit different, but if we think about the standard definition for block encoding nowadays is, let's assume you have the n-qubit matrix, which means that the size of this matrix is capital N. And if we can find two parameters, alpha and epsilon, these are positive real numbers, and m plus n qubit unitary matrix, which of this is this bigger size that I said. In the corner, there will be your A, but we need an extra information, and this m is actually the number of ancilla qubits, such that the following property holds. So what it says that this matrix U, this unitary matrix UA, it should be bolded, is the unitary, it's a block encoding of matrix A if this property holds. So we call it the alpha M epsilon block encoding. So alpha is the alpha corresponding to the fact that we have to have a bounded 2 norm of your matrix. You can always scale this alpha to be 1. M is the number of ancilla qubits that you need extra to be able to do this block encoding, to actually create this unitary matrix. And epsilon is the kind of the precision. Right? Ideally, we would like to be able to do epsilon equals 0, and that will be called the exact encoding. So exactly encode your matrix, and it is possible. But sometimes we are happy with the epsilon block encoding because of the applications and the fact that it's enough and it's easier. So we can do first, like to just verify if this definition makes actually sense, is that, okay, we can actually think about if the objects have the proper nature. So this one is, you know, just a very specific matrix with specific blocks. Then we have row block matrix, vector block matrix, and then if we look on this object here, if we don't have you know, any problems, and we have actually exact block encoding, if I look what this whole thing is, this should give me A if UA is the block encoding of the matrix. So just a sanity check, as we call it. So if we want to talk about some objects, always the most important question as I think any scientist is the existence and uniqueness, okay? I'm trying to determine something or create algorithm for something. It's better for me that this thing exists, and it's even better if it's unique. Okay, so there was a theorem by Albert and co-authors in 2003 which said every non-unitary matrix A can be embedded in the norm of A, so this is your alpha, 1 block encoding, so essentially epsilon is equal to 0, and 1 is 1 extra ancilla cubic. So this is the theory that tells us that any matrix can be block encoded. So we can assume, so here we are assuming that we are scaling this alpha to 1, so such that the norm of the matrix is bounded by 1. Otherwise, we just modify our matrix to be A over alpha. And we look on this classical singular value decomposition of this matrix. And of course, there is some issues. Oh, I'm sorry. This dot, which you see, should be a sigma, and I don't know what has happened to it. Sorry, I will correct that. But this is a classical singular, so singular value decomposition. I had to change the notation because U is now a unitary matrix. So we have the classical singular value decomposition, and then if you look on this, you will get what it is. This, you can check, it has a proper structure, it's your matrix and some things, and this matrix is unitary, and actually you can check that it satisfies the definition of the block encoding, okay? So some very simple examples of block encoding to see, okay, these things are possible. One of the trivial examples, if you have a unitary matrix, the unitary matrix is obviously a 1, 0, 0 block encoding of itself. So it's exact block encoding with no extra ancillary qubits if its norm is bounded by 1. If not, we scale. Okay, but if we have unitary qubits, we know already how to put it in the quantum computer. So then we have a very simple how to put the scalar, which is the most trivial example of the matrix. So it's 1 by 1 matrix. And we see that using the proof from before, this is essentially the 2 block encodings, which immediately answers the question of the uniqueness. You can find 2 block encodings for the same matrix. And then, of course, this will result in the fact 1 block encoding may be very easy to find, but very hard to transfer into quantum circuit. The other one, you may want to have to work harder, but it may be better suited for what you're trying to do after, so create the circuit and actually evaluate the algorithm. All right. So this was for the scalar, not very sophisticated matrix. What happens if you actually have a matrix of arbitrary size that we are interested in? Well, you see that you can generalize this idea from the scalar to the matrix case. So you get, again, 2 block encodings. And great, we know that they exist because the existence theorem told us that those block encodings exist. But existence not all, because if I look on both of these encodings, it's extremely or almost impossible to put them into the quantum circuits because it requires the square root of the, essentially this matrix. And there is no algorithm up to, you cannot do it efficiently in quantum computer using the polynomial Venn quantum gates. And it's too expensive. So I know that the block encoding exists. I can write it down explicitly, but in order to create a circuit, it's too expensive. Okay, so what can we do? So the theorem does not, so the theorem that we just presented, it guarantees there's an existence of the block encoding, but doesn't guarantee the existence of the efficient quantum circuit implementation. Question, yes?
When you say that, do you assume that you have an approximation of the matrix?
So the question was if I'm assuming that I can have an approximation. So here I'm looking of the matrix itself. A is arbitrary. So it can be approximation of some operator or like, you know. But here when I'm thinking at the moment, I'm thinking about can I get exact, because if you look on this theorem, this theorem assumes, as you see, the exact block encoding.
That's the question. So is it also fully true for the approximation?
No, that's why for the block, if you have an approximation, you're in a much better situation. So if I will, and I will talk about that, if you allow yourself encoding up to epsilon, then that's the way how you overcome the problem with the circuits creation. So that's why we have to do that step. But this is a very good question. Yes. Here I was like, theorem tells me there exists and I want to use it. Yes, I can write the block encoding, but there is another step 2, which I have to be able to realize. Okay. So there is some good news. Good news in the sense we can look at this certain structures of the matrices, and we may be able to construct different block encodings that are more suitable for quantum circuits. And as the question pointed, if I'm able to relax on the fact that I want an exact block encoding, then I'm also in the better position, and I will be talking about that now. Are there any questions in the meantime? Yes.
Maybe on the slide where you show the UA implementation, I didn't understand why there's a measurement symbol. Is it a kind of post-selection?
Okay, so essentially, I will talk. So the question is why I have a measurement here. So I'm thinking about this picture more and applying this block encoding to a state, so to a vector. So we will see this picture again where I have the measurement because I will be looking actually on the application of this block encoding, so application of the operator to the, but it's, yeah, it's right question. It's just that I'm thinking about applying it to the, and I will talk about how actually realization of the block encoding in a second. So, actually the work is from, Daniel Kamps and his co-authors Chao Yang and Rolf Verbunen have been working. Actually, there is a prior paper which was looking on the block encodings of the sparse matrices. I think it got now published in 2022, but there is a relevant also discussion in the paper about the package that they developed at the Berkeley lab that does the block encoding, and that's from, I believe, 2022. But these are the names which are relevant. So they look on let's look on the simple case. We have 2 by 2 symmetric matrix, again, structure. And so for here, we will just consider this matrix as a simple example, which satisfies our norm of the matrix condition and so on. And we can, it turns out that we can block encode this matrix A using as this one, where we have the block encodings. The following blocks are also the unitary matrices of this structure, with the beta 1 and beta 2 depending on the alpha. So this is you take a matrix, this is how you can write the block encoding. So this is kind of the general simple idea. Okay, we have this, and we know that how to do it for 2 by 2 symmetric matrix. Again, 2 by 2 symmetric matrix is really not bringing us far in terms of application. But this construction can be generalized to higher dimension. And how we can do it. So if we now remember about these parameters here, we had alpha 1, alpha 2, beta 1, beta 2, when those beta 1 and beta 2 are connected to alpha. You probably already see where I'm going here, but if I define phi 1 as some geometric functions on alpha 1 and alpha 2, then you can block encode this matrix UA using the following unitaries. So each of these matrices is a unitary matrix, and each of them, it's a little bit, some of them are similar. So if you look on U0, and it's the same as U6 and so on, so you need probably a moment to process this. But what the idea is, this is essentially a product of unitary matrices, and each of this matrix can be expressed by our very, very familiar basic unitary. So we have the Hadamard, the identity. These are the rotation matrices. Then we have the Pauli, X-Pauli matrix, and we have the classical projectors. So E0 and A1 are projectors using the standard basis. These guys immediately transfer to quantum circuits. So since we have quantum circuits for those, we can always determine the quantum simple circuits for all of those. We get UA. So if we look at the end, and I hope that this picture is, I had some issues with generating this picture. Some things were disappearing. I hope it's correct. So exercise for until Thursday. You can verify, but this is essentially the quantum circuit associated with this encoding. So you see your Hadamard, you see your rotation, you see your Pauli matrix, X-Pauli matrix here, and so on. So you note that the unitary matrix that encodes 2 by 2 matrix is of dimension 2 to 3 because we need, this is 1 qubit system, you need additional ancilla qubits to make it, right? This is your system. This is your system register, and these are 2 extra ancilla qubits that enables you to do that. So the system cube, it has to match the dimension, And the dimension of the matrix is n2 to the power 1. So what you can see is, remember we looked on this kind of simple example in the prior slides when I told you, oh, these are the quantum encodings, but there is no efficient way of doing the quantum circuit. Well, if you see, we have a quantum circuit, but it is twice the dimension of the block encoding given by the approach using the square root. So now we have a corresponding circuit, but the dimensions grew. And that's what we have to pay for. If we want to get the block encoding, we may have to pay in terms of dimension, or we may have to go into approximation of order epsilon, if we want to really realize that on the quantums, having a quantum circuit. But this is a quantum circuit. We can go to our colleagues who do simulations. They can build that into hardware. So we have all the components. Okay, so this was like 2 by 2. Wow. So what we can do further? So most of our applications, we are always interested in sparse matrices. Sparse representations are great. Usually they're more efficient, and we know how to discretize a lot of our infinite dimensional problems, differential equations, partial differential equations, such that we have a sparse representations of our operators. So what was, hard to say, the state of the art, how to block encode a sparse matrix. So let's just assume we have S sparse matrix, so we have some kind of structure in terms like the number of non-zero entries is S. So we know that we only have to encode NS entries into the quantum computer. So the initial work by Berry, Childs, and followed up with a number of collaborators. So it's 2009 initially, and then 2017 kind of continued. Is you think about also how the computer scientists are thinking about encoding matrices. Those of you who had some education in data data structures and things like that, they have various ways of encode the matrices, column-wise, row-wise. Sparse matrices, usually we introduce encode by the location. So row and column index of a non-zero entry and a non-zero entry per se. So they kind of went the same way. Is there a possibility of creating an oracles that will allow us to do that? We encode the position of the non-zero entry, and we encode the entry. And this is done by those 3 oracles, oracle row, so O row, oracle, and OA for the entry. And then we actually, okay, this is for one single entry, and then we have to combine these query oracles into what we call matrix query oracle to enable access to the whole matrix data. So this is how you will do it to access in 2 steps to enter your sparse matrix information into the computer. Okay, so if we think about S, so here we think about the matrix which has S non-zero entries. And we say that we have n plus 3 extra, so we have n plus 3 extra qubits, and we're allowing the approximation. So this encoding of A can be constructing in order of 1 queries to above oracles. So it's essentially how we can do that. And this is the number of gates, primitive gates, so the like simple gates that we will need to do this. Okay, so of course this is not feasible or not very efficient if you have a lot of non-zero entries, but then we don't call the matrix sparse anymore because it's becoming more dense than a sparse matrix. But it can be done, and it depends, of course, on the number of non-zero entries and on the accuracy. So if you want to if you're willing to sacrifice the accuracy, also the number of gates or the depth of your circuit will reduce. But what I wanted to talk about is an approach which kind of allows us to go into this like black box or really general framework. And it was introduced actually by the same group. So this is a paper by Kamps and Van Bumen from 2022. This is actually it's a package also that you can use. I think it's integrated also. It has it's available in QML, so we can use it with Qiskit. It's compatible with their own package which is called QLab. It's a MATLAB package for quantum computing. And the approach is called FABL, which stands for Fast Approximate Block Encodings. So you see already we are talking about approximate, so there will be some accuracy that we are paying, but essentially the approach is general. You can encode any matrix of choice. So it generates a quantum circuit that block encode arbitrary matrices up to the prescribed accuracy. So you as a user can prescribe the accuracy, and of course it will generate you the circuit, but depending what accuracy you prescribe, you may see it in the depth of your circuit. So that's something that you have to decide as a user, which is completely natural way of doing things. So it defines a matrix query operation for a given matrix, and then it's synthesized immediately to the quantum circuit. So with respect to the previous approach that I mentioned, it's not saying, okay, we have oracles which encode the entries and their positions, and then we build a matrix query, but it actually defines the matrix query immediately, and then it gives you a corresponding circuit. So let us define this matrix query operation. So given a matrix, the matrix query operation O of A, when we apply it to the classical, we have the classical, so the basis and we have an extra ancillary qubits and so on. This is how the result of this unitary of this operator will be. These are the n-qubit computational basis states. Okay, so these are the binary representation of your basis. So this is how it will be done. So we see that these are essentially scalar values for AI, JI, the entries. So this is how we can think about the extracting the entries or looking on the entries of this matrix query operation and giving us the representation of the matrix. Okay, so this is the high-level circuit again, and here we think about how I can actually create this matrix query and then using it to apply it to the matrix, because if I'm thinking in terms of possibility of kind of computation in terms of like matrix vector products or operator state evaluations, this is how we are going to think about it. So you have your set of extra ancillary Qs, you have your state. This is how this structure of the FABL block encoding of the matrix A and applying it to the state psi will look like. So you have this query, matrix query. Here sitting, you apply, you have your input state, and then you measure, and if you measure 0, of course, then you expect that here you will have an application of your matrix to a vector, which means the block encoding actually of the matrix into your initial state. So all information about the matrix are encoded in a single matrix query oracle. So you don't create those 3 queries for positions and for the entry separate, and then you build the matrix query. Everything sits in one. And they can be implemented with a simple 1-qubit rotations, 2-qubit control node gates, and some additional Hadamard and swap gates. So they're completely able to, we are completely able now to create those matrix queries and express them in terms of simple gates that we can then use in practice. The gate complexity, which is important, of the FABL circuit for general unstructured matrices is bounded by n squared. So this is the size of the matrix squared. But this is without any additional information on the matrix. So of course, if you have more structure, they discuss how you can do it, for example, if you have a certain sparsity pattern or something more efficiently. And there is a prefactor 2 for real and prefactor 4 for complex matrices. So it's a little bit more expensive to do it for complex matrices. Plus the limited polylogarithmic overhead, but that's from, it's not substantial, but this is the general complexity. Okay, so we have the circuit that I showed you, and how we can verify that actually the circuit is 1/2 to the power and n plus 1 encoding of the matrix. Well, we check our definition. So remember, this is the block encoding written using this matrix query oracle. And we want to check if it satisfies the definition of the block encoding. And we can do it, so we have the Hadamard application multiple times, then we have a query oracle, then we have the swap operation, and then if you combine all of this, you will see that actually, okay, this is up to the scaling factor, the entries of your matrix. So this is a correct block encoding of your matrix A with arbitrary ij entries. It's a very well written article about Fable and it's and the corresponding package. So I encourage those of you working in this area or interested in how to actually put data in to have a look. Since there was a mention about the other rotation gates that we need, we will talk about rotation operators. We will actually talk about the rotation operators more, but how this oracle query. So remember, we say, okay, there is matrix query O of A sitting here. Well, how does this look like? Because it's encoding of the matrix. Well, if we define the rotation matrix along Pauli Y matrix and define the theta ij's as the R cosine of the entries of the matrix, we will see that for the real valued matrix, this is how your matrix query looks like. So it has essentially the cosines and sines of this, which are connected to particular entries of the matrix. So this is how this matrix query as a matrix can be represented. And if you're interested in details, you should follow those two papers and their associated package of and Fable. So the package also, you give the matrix, it spits out essentially the quantum circuit associated with the block encoding, and you can specify all the information you want to. So as I mentioned, and I want to talk about it because I will use it tomorrow, Thursday, in the second, yeah. Oh, sorry.
Just so that clarifies my understanding. So the usefulness of the matrix algorithm is then if you're able to define the oracle easily, then you have an easy way to define the block encoding.
Exactly. So you can define it in this way. They specifically tells you this is, if you have a matrix, you know how to do the query oracle. But in terms of general approach, if you're thinking, okay, what is the benefit? If you know, and previously it was done through, first you went through the oracles for the positions and the entry, and then you were kind of working with those to get an equivalence of this, so the matrix query oracle. So now you're kind of skipping those additional steps, oracles, and you can directly go to matrix query immediately. So, as I said, block encoding, which we use now and how we call it, you may see it in the literature as a standard form encoding. And the standard form encoding was introduced by Low and Chang in 2019. And in particular, they were interested in Hamiltonian simulation, and that's how they were looking how to represent the Hamiltonian. but it's you can think about it at very particular, it's a more general setup with respect to what I showed you. In a sense is, if you have an operator, and in their case, they were looking at Hamiltonians, acting on a certain Hilbert space, so there's Hilbert space involved, and you want to create a block encoding, or what they call standard encoding, that maps essentially a pairs from this between the chronicle of those spaces, so from one state space to the other, for an auxiliary Hilbert spaces. And you have a unitary state preparation oracle, so you have access to this. So G, you can think about it, okay, if I think about this is a vector, so it's essentially a mapping. So this is a column vector, and you have a G, which is some operator that you want to, this is how they define the standard encoding. So if you think about this definition and the definition of the block encoding we saw, there is, in the block encoding, this is essentially this one, because it's chosen very specifically how this G is defined. But you can define it in a more general setting, depending what your Hilbert spaces coming from your nature of your problem are. So as I said, they use it for specific Hamiltonian simulation, and I will actually give you an example on Thursday where we will use that particular representation, because the way how our example Hamiltonian is constructed. So if you see standard form encoding, that's essentially the same thing, and sometimes you may see calculations done using this G, so don't be scared, it's the same definition, it's just covering a little bit broader, a broader setup in terms of nature of your input data. Okay, so as I mentioned at the end, the goal is to be able to apply the operator to the state or matrix vector product. So we have a block encoding, and we want to apply it to an extended vector. So we have our state, but we need to have an extra ancilla qubits to do it. And how do we do it? Okay, we apply this to an extended vector. So we have our state that we actually want to apply the operator to, and we have extra information, so coming, so extra zeros in this vector to make it fit also in terms of dimension, because you have now bigger representation of your operator. So if you apply now your block encoding UA into this extended vector, so this is how you do it, you know, if you think in terms of matrices, you'll see, okay, I do this, that's what I'm getting. I'm getting what I want. I want an application of the matrix to my vector, so the operator to the state. And I get some garbage here. But now, okay, you can decompose it and see that this is okay. This is actually the part that I'm interested, and this is some extra stuff here that is unnormalized there. Usually they call it garbage. But this is essentially what you're expecting to see. So you get the product A times the state psi by measuring the ancilla qubits. And if the ancilla qubits are, so that was the picture, that's why the measurement was there. If you measure here this qubit to be 0, then you know what you get should be the application of your operator to the state. So provided that the application on the first wire is 0, and the success probability of this measurement is here. And one thing that I want to comment on, that I want to comment on, we had a discussion. If you look on the condition for the block encoding, it tells you that the norm of the matrix has to be smaller or equal than 1. And then that the probability of this measurement is proportional actually to the norm of this dividing by alpha. And we had a okay, what if you kind of have the matrix, of course the only case that the matrix norm is 0 is that it's a 0 matrix. But it's kind of interesting when you think about this in terms of this probability of measuring. The probability is proportional to this norm. This norm is 0, so you measure something with probability. So this matrix product the success probability of this measurement will be 0. But it's a kind of very bizarre example. We are not block encoding zero matrix, and no one is actually interested in doing computation with zero matrix. If your matrix is 0, you know what the outcome is. But this is somehow like how definitions, you have to be specific. There's actually some conditions of the elements being like, you know, they have to be bounded because that's what it means in terms of the norm of A. But, you know, we are not considering zero matrices for block encoding. They're not interesting, but yeah. All right, so if we want to kind of get a summary, quantum versus classical numerical linear algebra. Okay, in the classic case, the state space, 2 to the power n, okay, n is the number of qubits, it grows. So you can imagine if we are working with, you know, even 2 to the 10, 2 to the 16, I mean, this is not feasible. Space elements, okay, we have n-dimensional vectors, again, to the power n-dimensional vectors, really large objects to work. So the polynomial cost and the size of the matrix, we know classical algorithms are, you know, QR algorithm n to the cube. Okay, it's polynomial, but it's n to the cube. And if n is large, n to the cube is, you know, it's large. We can get entries to the vector. This is easy. We can do any kind of matrices. We can copy information. So here we are happy. In the quantum, okay, the state space dimensions n in terms of the number of qubits. We have the cost, which is, you know, polynomial in the number of qubits. So it's slightly different, and that's where the hope is of getting a gain. But in terms of other aspects, we have to work harder for the states. We have to work harder for operators, and we are limited to unitary. We cannot copy information. So there are some good news and some bad news. That's why it's evolving field. There's lots of things we have to think about, which we don't have to think in terms of classical numerical linear algebra. But that also makes the journey fun. And so what I will start, I guess, tomorrow, and I think I will revise this because you have heard already about certain things that I had on my slides today, so I can actually move faster to the other parts, is I will talk about some essential computing toolbox. You have learned already about something, and then I want to talk about fundamental linear algebra problems in scientific computing, and I will focus on eigenvalue problems, but I will focus of how we can do one of the most powerful techniques in numerical linear algebra, and how we can look on the quantum version of this, namely the Krylov subspace or subspace projection methods, which are very, very powerful and can be used in arbitrary context. So that's the plan for tomorrow. And I think I'm good on time, so I will stop here and take questions.
Okay. So thank you. And if you have some questions.
Thank you so much for the nice presentation. So my question is about the practical use of block encoding. So I can see that maybe when we are using block encoding, we assume a full tolerant quantum device. So what are the challenge or solution when it comes to use block encoding on near-term quantum device?
So the question was that the block encoding, if we what if we have a new the NISC technology available in terms of accuracy? I mean, the concept doesn't require the access to the full tolerant machine, right? This will be the additional error that you have to consider if you do the block encoding. And then that's why we're thinking about the block encoding up to epsilon approximation, because we may not get it exact. So people have, people are using those in computations. They're doing simulations and so on. Of course, everyone is waiting for the full tolerant machine, but as we heard this morning, we still do the calculations, and the concept itself of block encoding theoretically it doesn't limit us on the full tolerant machine. Of course, when we think about circuits, then it's we have to deal what we physically have available in terms of hardware. So there is nothing that we cannot do, but we have to take that into account, what we can get from the hardware, what our hardware is capable of.
Is there other questions?
I think here up front.
So it's a question online. You presented several situations in which you can apply block encoding. Could you please just sum up those different situations and the difference in the application of the algorithm?
So I presented kind of a way how the block encoding. So the question was that I talked about several different ways on block encode the matrices. I think I will say that the concepts actually are, I introduced what was or what is the state of the art for sparse matrices, and this will be done still on many applications. But then I moved to this Fable, which Fable seems to be at the moment very promising because it allows us to block encode an arbitrary matrix. So I will say that depending what the person who asked the question goal is, if for example you are working with some specific Hamiltonian system and so on, that there will be a better way of encoding your operators or your data into the system. However, if you think about really black box application or data machine learning applications where your data cannot be connected to any like quantum physics or something that has more structure, then I would say your best way of looking at that is using Fable and try to just encode your data into there and look on the circuits and then look again, but because you may be able to process it further and optimize. But this is kind of the most generic approach I would consider for applications at the moment. I hope that answers the question.
Thank you.
Thank you. Is there other questions? No, because remotely is
Thank you very much for your talk. I have two questions. First, what do you mean by copying the information when you compare quantum computers and classical computers?
Mm-hmm.
And second, are there other methods for different types of inputs other than matrices, like features or probabilities?
So for the first part, copying information. So when we think, I'm thinking in terms of, so the first question was about what do I mean by copying, creating a copy of the state or copy of the matrix. And then the other question was about can we consider different type of inputs than vectors. So first question number one, it's more related to what we can store on the way. So if you think about even doing, and I will talk about that on Thursday, when you think about, you take your classical algorithm for even iterative, you generate, for example, your subspace basis. I will talk about Krylov, so if you're not familiar, there is no problem. But you try to take a big problem and project it on the smaller space. In order to project this space, you need a basis. In order to take a basis, you have to store things on the way. So you evolve, you apply your operator to your state, and then you have the result. And I need this result later on. What I'm going to do with it? I mean, it's not going to hang anywhere. I can measure, and I know what it is, but I have no way of like keeping the history back, which is very limiting. In terms of which I can easily do in the classical way. And the second part about the inputs, I think, so for me, the vision is always, I think, in terms of applying I want to store the data which have kind of no structure that I can exploit. So that's kind of the most general. But as I said, if we have particular applications, then, if you have a Hamiltonian, for example, as we saw this morning, which is naturally a linear combination of the Pauli matrices, then you don't have to do any block encoding, and you can just, you have a state that you want to evolve, and you have a natural way, kind of explicit way of representing. I'm not familiar, but I don't know if anyone is working more on the stochastic or probabilities. I mean, everything has to come as a state. So if you're able to input this, construct, like transfer your input data, whatever they are, for me it's a vector. But if it's a probability or something else, you have to be able to do it, to turn it into a state. And I think that's what it's called the state preparation. If you're able to do it in an efficient way for a very particular information that you want to put, like you said, probability or something, then you're good to go. But I'm thinking like, in lots of this algorithm that we are thinking about, we are working with random starting vectors or random inputs and so on. So we have to be able to kind of construct a state which is equivalent to that. But I think it only depends how the state preparation for you will look like, because it has to be a state. And so that will be my very general answer. But I would prefer to someone who is more expert on this different approaches and so on, because for me it's I think in terms of numerical linear algebra, and I have a vector, a matrix, operator, function, whatever. That is my input, but I would assume that it's possible as long as you can create a state that is representing what you want to input.
Thank you. So I think we'll thanks Agnieszka again.